Now that we have our environment synced, let's look under the hood. In a traditional database, you're looking for exact matches, a username, an ID, a timestamp. But in a vector database, we're hunting for vibes, or more scientifically, mathematical proximity in high-dimensional space. When you input a query, the model converts it into a vector, and the database calculates the distance between that point and every other point it stores. We usually use cosine similarity here because it measures the angle between vectors rather than their length, which is much more effective for capturing semantic meaning in language. To keep this fast, we can't just check every single vector. That's a brute force search, and it's a performance killer. This is where indexing comes in. The first major player is IVF, or inverted file index. It clusters your vectors into Voronoi cells. When you search, it only looks in the most likely cells. It's fast, but you risk losing a bit of accuracy if your neighbor is just across a cluster boundary. The heavy hitter, though, is HNSW, Hierarchical Navigable Small Worlds. Imagine a multi-story map. The top floor is a very zoomed-out view with only a few landmarks. As you drop down through the layers, the map gets more detailed. It allows the database to skip 99% of the data and find the nearest neighbors with incredible speed. If you're building for production, HNSW is usually your default choice. Let's get practical. You can't just throw raw text at a vector DB. You need an embedding pipeline. We're going to use the sentence transformer library with the all-mini-LM L6 V2 model. It's lightweight, fast, and perfect for local testing. Watch the screen. We're batching our data into groups of 32. Why? Because sending 10,000 individual requests to an API or a local model is a great way to crash your script or rack up a massive bill. We normalize the output so that all our vectors have a magnitude of 1, making our cosine similarity calculations much more efficient. Here is the pro tip that separates hobbyist apps from professional tools. Metadata filtering. Searching by vector alone is powerful, but sometimes you need constraints, like find me articles similar to this one, but only from the year 2024. By attaching a JSON metadata object to each vector, we can perform a hybrid search. The database uses a traditional B-tree or hash index to filter the metadata first, then runs the vector search on that subset. This drastically reduces latency and ensures your results are actually relevant to the user's context. A quick reality check. More dimensions aren't always better. If you use a model with 3072 dimensions, your search will be more nuanced, but your memory usage and latency will spike. If you're building a simple chatbot, a 384-dimension model is often plenty. Don't over-engineer your architecture on day one. Start lean, measure your recall versus your latency, and only scale the dimensionality if your search results are consistently missing the mark. In the next part, we're going to wire this all into a fast API backend to make it accessible to the world. Let's talk about the elephant in the server room, memory. If you're storing 10 million vectors at full 32-bit precision, you're looking at over 60 gigabytes of RAM just for the raw data. And that's before we even talk about the overhead for the HNSW graph. This is where quantization becomes your best friend. By using scalar quantization, we compress those 32-bit floats into 8-bit integers. It's like turning a high-res WAV file into a high-quality MP3. You lose a tiny bit of mathematical nuance, but you slash your infrastructure costs by 75%. If you're operating at a truly massive scale, product quantization takes it further by breaking vectors into subspaces and using a codebook to represent them. Memory is expensive. Don't pay for precision you don't actually need. Building the search is the easy part. Knowing if it actually works? That's where most devs fail. You can't manually check 10,000 queries, so we use frameworks like Ragus or Arise Phoenix. We use a more powerful model like GPT-4o or Gemini 1.5 Pro to act as a judge. The judge looks at the retrieved context and asks, did the database actually find the right information? And did the chatbot hallucinate based on that info? If your context precision is low, your vector index is failing. If your faithfulness is low, your LLM prompt needs work. Stop guessing and start measuring with a systematic evaluation pipeline. In a static demo, you load data once and you're done. In the real world, data is a river. When you upsert, which is just a fancy way of saying update or insert, the database has to integrate that new vector into the HNSW graph or the IVF clusters. This is computationally expensive. If you're building a news app or a real-time stock analyzer, you need a database that supports incremental indexing. Avoid databases that require a full rebuild of the index every time you add a few rows, or your latency will look like a mountain range. Always check the right latency specs before you commit to a provider. The coolest part of this journey? We aren't limited to text. Using models like CLIP or SIGLIP, we can map images and text into the same vector space. This means you can search through a library of millions of photos using a text prompt or find similar images without a single tag or caption. The math is identical, only the encoder changes. As you scale, think about how multi-vector strategies, where one object has a text vector, an image vector, and a structured data vector, can create a search experience that feels almost psychic. We've covered the math, the indexing, the compression, and the evaluation. To wrap this up, remember the golden rule of vector search. Your search is only as good as your embeddings. If you switch embedding models, you must re-index your entire database. You cannot compare a vector from OpenAI with a vector from Hugging Face. They speak different languages. Build your pipeline with modularity in mind. Keep an eye on your memory consumption, and always, always validate your retrieval quality. You've got the blueprint. Now go build something that actually understands the world.